HMAC or hash-based message authentication code lets you combine a secret key with a cryptographic hash function to generate a message authentication code or a MAC that proves the message is authentic and untampered with. Say you're receiving webhook events in your application from your trusted payment processor like Stripe. How do you verify that the messages actually came from Stripe and not from an attacker spoofing their servers? To prevent this, Stripe shares a secret key with you in your dashboard. And then along with every incoming webhook, they include a message authentication code or a MAC, which is generated with an HMAC function like HMAC SHA-256. Under the hood, HMAC mixes your secret key with the payload of the message and hashes it twice. When your app receives the request, it computes the MAC using the shared secret and compares the result with the received MAC. In Python, for example, you implement this using HMAC module from Python's standard library. If the two values match, the message is authentic because only you and Stripe share the secret. Notice one very important detail here. We use compare digest function and not a standard double equals comparison. That's because the normal string comparison checks two strings character by character, and as soon as it finds a mismatch between two, returns false. This small optimization exposes your application to a timing attack. If an attacker sends a fake signature starting with 00, your server rejects it in 1 millisecond. If then they try 01 and it takes 2 milliseconds to fail, the attacker knows 01 matched the first byte and force your code to move on and check the second byte before failing. So by repeating this process thousands of times, an attacker can forge the entire signature one byte at a time. Okay, now once you know what HMAC is, you notice it everywhere. For example, the 6-digit code in your Authenticator app is the HMAC of the current time and a shared secret. Keypairs. A key pair consists of two mathematically related keys, a public key and a private key. As the name suggests, the private key stays strictly secret while the public key can be safely shared with other people. Anything encrypted with a public key can be only decrypted by its matching private key, and it's computationally infeasible to drive the private key if you only have the public key. So if you can decrypt the message that is encrypted by the public key, that authenticates you as the private key holder. Take SSH as a real-world example. You can use algorithms like RSA or Edward Curve's digital signature to generate a set of public and private key. As a side note here, if you're generating a key today, just use Edward Curve's digital signature. It provides shorter key, faster performance, and you don't have to decide the key size to get it wrong. When you set up the server, you copy your public key into the server's authorized keys file. Now when you try to SSH in, server sends you a set of random bytes called a challenge. You hash the challenge and sign the hash with your private key and send back your signature. Server check your signature against your public key. If it matches, server authenticates you and you're logged in. And of course, this only works if you have a few machines. But in the real world, the authorized keys files doesn't scale. Let's say an engineer leaves your company. Their public keys has to be removed from authorized keys on hundreds of servers they SSH into. So at scale, nobody really manages authorized keys files by hand. Instead, all of the servers are configured to trust a single public key, and that's the public key of your internal certificate authority. So when an engineer needs access, the certificate authority signs their public key and issues a short-lived SSH certificate for them. This is what identity tools like HashiCorp Vault and Teleport do under the hood. And to understand this, we need to understand the digital certificates. A digital certificate is essentially your public key bound to your identity and an expiry date, all signed by a trusted certificate authority or a CA. X509 is a universal standard that defines what a certificate must contain, which are 5 core elements: your public key, the subject or who you are, the issuer or the certificate authority who signed it, not before and not after, which define the interval during which your certificate is valid, and the certificate authority signature itself. When you visit a domain over HTTPS, your browser needs to first confirm that the server holds the private key for the domain you requested. So server presents its certificate to you during the initial handshake, which was obtained ahead of time by sending its public key and identity to a certificate authority in a form of a certificate signing request or CSR. Historically, this was a manual process that you have to pay for it. but today most of web does this automatically and for free using Let's Encrypt and ACME protocol, the automated certificate management environment. So basically your server proves control the domain that you're asking a certificate for and get issued a certificate valid for only 90 days. Tools like CertBot, Caddy, or Cert Manager handle certificate issuance and renewal without your intervention. Once the server has the signed X509 certificate, verification is fast. Your operating system and browser come with a list of certificate authorities they trust and their public key is pre-installed. So your browser hashes the domain certificate and check the signature using the CA's public key. If the signature matches and dates are current, the browser authenticates the server and establishes an encrypted connection. JWT, a JSON Web Token or JWT, consists of three base 64 URL encoded parts: a JSON Web Signature or JWS, the JWS payload, and JWS protected header, where each part being separated from the next by a single period character. Both the header and the payload can be decoded by anyone because they're not encrypted, and they include parameters like algorithm used to produce the signature, the subject, the recipient, and the expiry timestamp of the token. The signature part of the token represents the content of the token, secured either by a digital signature or a message authentication code, depending on whether a Keypair algorithm like RS-256 or a HMAC algorithm like HS-256 was used. Because the JSON Web Token itself carries the payload and the signature, it can be parsed and validated by anyone who have access to it directly, without them having to look up a database or involve the issuer server. For example, take OpenID Connect and sign in with Google. After your user authenticates with Google, Google creates a JWT and signs it with its private key. Then when your server receives the token, it reads Google public key from Google JSON Web Key Set endpoint and use it to verify the Google signature on the token. mTLS, mutual TLS or mTLS, is used when during the communication event, both client and server need to have distinct identities and perform mutual authentication. And for that, client and server hold digital certificates signed by a certificate authority that both sides trust, and that carry their identity in the subject name field. Say you have two microservices deployment in a Kubernetes cluster and you need them to mutually authenticate before they communicate. One way to achieve this is to use a service mesh like Istio. When configured, it deploys the sidecar proxy next to your service container on both sides. The proxy comes with a digital certificate for your service and the cluster certificate authority public key baked into it. Now, when service A wants to connect to service B, it sends a request to its proxy first, and the proxy opens the connection to service B's proxy on its behalf. During these connections, both sides request the other side's certificate, verify the identity and the signature on the certificate, and only if authentication was successful, establish a connection. Workload Identity Federation. Workload Identity Federation lets a workload on one platform authenticate to another platform using its own platform issues identity. Say your GitHub workflow job needs to push an object to an SRE bucket on your AWS account and you don't want to generate and store a long-lived AWS access key. With Federation, the platform running the workload, in this case GitHub, acts as an identity provider. So every time your workflow job runs, GitHub's OpenID Connect provider generates a JSON Web Token for that job with information like the repository and the branch. Then sign the content of the token with its private key and your workflow sends the JWT token with the signature to AWS. Ahead of time, you configure your AWS account to trust GitHub's OIDC provider as a federated identity. So once AWS receives your workflow's token from GitHub, it fetches the public key from GitHub JSON Web Key Set endpoint and verifies the signature and other claims on the token. If everything checks out, AWS issues temporary credentials that your workflow job can then use to push the objects, and those credentials expire on their own. OIDC Federation that we just saw is the cloud version of this idea. If you need Workload Identity Federation for your own infrastructure, SPIFFE or Secure Production Identity Framework for Everyone is the standardized version. And that gives us the 6 different authentication concepts that I think every engineer should know. If you learned something from this, consider subscribing. I explain topics like this one on this channel.